We are in Unit 11 and this is Notes 3. Today we are going to be looking at the integral test and the p-series test. So let's take a look at what we've done so far in Unit 11. So far in Unit 11 we started out with doing convergence and divergence of sequences. And we said a sequence is just a list of numbers, right? Just a list of numbers, and do they converge? Does that sequence converge or diverge? There's only one thing to do. Take the limit as n goes to infinity. If you get a number, then the sequence converges. If you do not get a number, so if you get infinity, negative infinity, or more than one number, key is a number, not some numbers, then the sequence diverges. Okay? And that's it. There's no other test for convergence, divergence of sequences. That is it, okay? I stress that because sometimes when we start doing a lot of tests for series convergence, kids forget about sequences. This is the only thing you do for sequences. Then we went to series. In Section 2, last time, we did convergence of and divergence of series using, first we did the nth term test, and in the nth term test, again, you take the limit as n goes to infinity. This time, though, if you do not get 0, then the series diverges. If you do not get 0, the series diverges. And that's it. That's all we know about the nth term test. That's all we can tell from the nth term test. The nth term test can never say anything about convergence because we just don't know. So if we do get 0, then we go and use one of our other 9 tests. Then we took a look at telescoping series. And in a truly telescoping series, they all converge because lots of the numbers will cancel out and you'll be left with, some numbers that you can actually add. So in a telescoping series, not only does it converge, but we can actually tell what it converges to. Okay? And then we did the geometric series test. And for a geometric series, we find what the common ratio is. If the absolute value of r is less than 1, then the series converges to this. So we can tell what the series converges to here, where this top value is the first term of the series. And if the absolute value of r is greater than or equal to 1, then the series diverges. And remember, a geometric series can be written in the form some number, I'm going to put it a here, some number r to the n. Just keep in mind that these a's are not always equal. They're equal if n starts at 0, but they're not going to be equal if n does not start at 0. You always have to find that first term. Okay, so that's what we've done in the past so far this unit, and today we're getting 2 more tests. I told you for convergence and divergence of series, we're going to get 10 tests total. So last time we were together we did 3 of them, and today we're doing 2 more. Okay? So before we get going, I always do a little bit of a review of, since the integral test involves integrals, and since a series does go to infinity, I want to do a little review of improper integrals that go to infinity. Okay, where one of the bounds is infinity. So I would like to compare this integral 1 to infinity of 1 over x dx. And I want to compare that with the integral 1 to infinity of 1 over x squared dx. And I'm comparing those two because they have vaguely similar graphs, okay? So the graph of y equals 1 over x looks like this. Let me get a different. The graph of y equals 1 over x looks vaguely like this, right? And the integral from 1 to infinity is the area under the curve from x equals 1 to x equals infinity. So we're going from 1 to infinity. So we're finding that area. And when we did improper integrals, this is improper because one of the boundaries is infinity. That was back in Unit 9, by the way, if you want to refresh further. Okay. Back when we did improper integrals back in Unit 9, we said sometimes this area is infinity. It looks infinite because this graph never touches the x-axis, right? How can it be anything? How can the area be anything other than infinity? But we found out back in this unit that we can get areas that are not infinity, that look like they are infinite. This graph over here, it looks a little similar. The graph of y equals 1 over x squared looks kind of like this. Okay? So it looks fairly similar. From 1 to infinity, it looks fairly similar. So from 1 to infinity, I'm looking at something that looks like that. Again, the area looks infinite because this curve never actually hits the x-axis, right? So when we found out, and let's go ahead and evaluate these integrals. It'll be a nice little review of improper integrals as well. When we evaluate this, I start by going ahead and taking the antiderivative, right? Well, the antiderivative of 1 over x is natural log absolute value x, which I want to put here, but I'm going to leave a space because this is improper. I cannot put infinity as one of my boundaries. I need to write it as a limit instead. So I'm going to write that as limit as b goes to infinity of the natural log of the absolute value x, that's the antiderivative, from 1 is fine, but I cannot put infinity up here. I need to put b up there. You can never put a value on a boundary that makes your function undefined or not a number. Okay? Now we put b in for x and let b go to infinity. Well, natural log of something going to infinity is infinity. Minus, now put 1 in for x. Natural log of 1 is 0. So we get infinity. We get infinity. And so this integral diverges. The integral diverges. That's what we said when we were doing improper integrals. Okay? Integral diverges means the area is going to infinity or negative infinity. Okay? All right. So that makes sense because it sure does look like it's going to infinity. But when we come over here to this one and do the same process, we do not get infinity. If we take the antiderivative of 1 over x squared, we get negative 1 over x using the power rule. So we have the limit as b goes to infinity of negative 1 over x from 1 to b. And this time when we put b in for x and let b go to infinity, 1 over a huge unbounded number is 0. This is going to 0. Minus, put 1 in for x, we get negative 1. So this area, not only is it not infinite, it's just 1. Okay? So, even though they looked similar, they clearly were not that similar. So let's take a look, and I know I did this back with you when we did improper integrals, but it's important enough, it'll help you understand series if I go ahead and go through this with you one more time, quickly. I'll try to do it quickly. Okay. So on our graphs, let's plot. Let's see exactly what 1 over x and 1 over x squared looks like. Get to where you can see it here. So I'm going to put 1 over x in for y1, 1 over x squared in for y2. I didn't do the 1 over. Okay, that looks better. Okay, and for our window, I only need to see from 1 to infinity for x. And I really don't want to go all the way to infinity. I think for our purposes, I just want you to see this graph. So I'm just going to do 1 to 10, okay? For the scale, that's fine. 1 is fine. For the y-min and y-max, I really don't need to see anything below the x-axis, do I? And when x is the largest y value here is going to be 1, because when x is 1, we get 1 here, and when x is 1, we get 1 here. So I'm just going to go for the minimum. I think I'm just going to show a little tiny bit, maybe negative 0.2, and I'm going to just go up to 1 for y. Okay? So now I'm going to graph this. The first thing that graphs is going to be 1 over x. The second thing that graphs is going to be 1 over x squared. So let's watch it graph, okay? In fact, let's watch it graph. Let's turn on our little bubble, huh? Where's our bubble? There it is. There it is. Okay, ready? Here we go. So there's 1 over x. And as x goes to infinity, 1 over x goes to 0, right? As x goes to infinity. So here's 1 over x squared. And as x goes to infinity, 1 over x squared is also going to 0. But if you notice, 1 over x squared is going to 0 more quickly than 1 over x does. If we went not to 10 but to 20, there's 1 over x. It's going to 0. It's going to 0, right? There's 1 over x squared. It's also going to 0, but just much more quickly. I'm going to say this when we're looking at series. I'm going to say, how fast does it get to 0? They both go to 0. So they both pass this, the nth term test. They're both going to 0, right? So they don't automatically diverge. We have to use another test, right? So they're both going to 0. My point is, how quickly are they getting to 0? Clearly, this one is not getting to 0 fast enough to converge. It's going to diverge. And that means that the series from 1 to infinity of 1 over x will also diverge. Okay? If the integral diverges, then the series diverges. If the conditions for the integral test are true, and we'll get there. Okay? If the conditions are true. If the function converges, then the series will converge. I put an X here. I just took a peek there. That should be an N because I'm using N's here. Then the series will converge. Okay? By integral test. Okay? So that's the logic. That's my rationale behind this. Okay? Here's what the integral test says. If f of x is positive, it has to be positive, continuous, and decreasing. Positive, continuous, and decreasing. Is f of x for your boundaries? We only care about the boundaries, right? From 1 to infinity. Is f of x positive? Yes, because it's above the x-axis. Is it continuous? Yes, it's continuous. There's no value in here that makes the function undefined. Is it decreasing? Yes, it's decreasing. So in many of these that pass the nth term test, which means that we cannot use the nth term test, in many of these your function is going to 0, so it's going to be decreasing. Okay? So positive, continuous, and decreasing. That's important. If your function is positive, continuous, and decreasing, then if the integral from 1 to infinity of f of x dx converges, then the series n equals 1 to infinity of a sub n converges where a sub n is f of n. So if you replace the x with an n, then it's the same. So replace the x with an n and you get the series. Okay? If the integral from 1 to infinity of f of x dx diverges, then the series diverges. So either both converge or both diverge. Okay? I could also switch these. So if the series converges, then the integral converges. And if the series diverges, then the integral diverges. And I'm using 1 to infinity all over the place. That's not important. It can be any number to infinity. It has to be going to infinity. Otherwise, it's not an infinite series. So it has to be going to infinity. But other than that, this bottom number can be anything we want it to be, as long as these have to be the same. The bottom value in the series and the bottom value in the integral are the same. Okay? All right. So this is the integral test. I'm going to go look at your notes in just a sec, and it's already on your notes there. Oops. Okay. That's the integral test. This first step, though, is uber important. Okay? So before you go and use the integral test, I need you to state this. You don't need to go through any big rigmarole to prove these. You don't have to prove these to me, but I need you to state this. Before you go and use the integral test, here's what I need you to say. F of x is positive. You can use a little positive sign is fine. Continuous. Sorry about that. Hang on. So f of x is positive, continuous, comma, decreasing. Just do that before you go and find the integrals. Okay? If you don't say this, then these mean nothing. Then you can find the integral, but that doesn't prove anything about the series. Okay? Without stating that. Sound good? So, every time, say f of x is positive, continuous, and decreasing. And in class, usually what I do is I tell the kids, repeat it after me, and we repeat it about 4 times. Okay, positive, continuous, decreasing. So if you want to pause the video right now and repeat that to yourself a few times, that'll be just fine. Alrighty. Very good, very good. Okay, so here's your printed out notes. So let's go ahead and switch to those. Get situated here. Let's switch to these. So I went through why this is true, in other words. So if f of x is positive, continuous, and decreasing on your interval, okay, then both the series and the integral converge, or they both diverge. Okay? All right. Let's go ahead. We've talked all about this. Oh, this is another great note to make. Okay, so also note the value of the integral. What we got, oh, this is a, let me go back to this that we did. You know how we got that in this one, I said that this series would diverge because the integral diverges. In this one, we got that the integral converged to 1. The integral converged to 1, right? I said that this series converges. Does it also converge to 1? No. Definitely not to 1. We know it converges. We don't know what it converges to. We do not know what it converges to. Let me stay on this little I'll come over here. I've got room over here. All right, let's come over here and let's look at the series from 1 to infinity of 1 over n squared. Okay, we know what the graph of 1 over x squared looks like. What does this? What if we were to plot points? What would this look like? Well, we'd have to start at 1, right? So we put 1 in for n and we get 1. Yeah? Put 2 in for n. What do we get? We get 1/4. I'm going to all ballpark that. Put 3 in for n. We get 1/9. Put 4 in for n and we get 1/16. I'm getting really close to the x-axis here, but you get the idea. It gets close to 0 fast, right? That's the phrase I want you to think of. It gets really close to 0 really fast. Okay? Now, this area here, if we were to connect these dots, the series, these are not connected in a series. They're just points. So we're asking ourselves, does this sum converge? So we're adding, I'd like to add this, plus this, plus this, plus this, right? I'm not adding up every little thing like I do in an integral. I'm not adding up everything, am I? Okay? So I'm actually adding up like 1 times this height, so 1 times this height, plus 1 times this height, plus 1 times this height, plus 1 times that height. I'm actually doing a left Riemann sum. And we know a left Riemann sum on a decreasing function will yield an overestimate, right? So this 1 here is going to be, it's going to be less than my actual sum. This integral that I get, this 1 that I got, that integral is less than what I want. It's less than it. Okay, how much less than it? Well, I know that, so I know that the integral from 1 to infinity of 1 over x squared dx is going to be less than that sum. I know it will be. It has to be. I also know what it's bounded at the top by. Okay? It's bounded at the top by the very first term, whatever the very first term is, plus the value of that integral. Okay? So for us, if we wanted to know about what this sum is, we don't know exactly, but we know what it's between. that integral was 1. My first term in the series was 1. So my sum is between 1 and 2. So there's no way, using the integral test, there's no way for us to find the exact value of that sum like we can with a geometric series test or a telescoping series test. We cannot find the exact value, but we can find a range that value must lie in. Okay? And that's what this says here in this box. Okay? All right. Let's take a look at some examples. In example 1, finally, gosh, what are we, 26 minutes in, and we're getting to examples. Perfect. Okay. Let's look at some examples. So, first of all, for this one, it's not geometric, it's not telescoping. If I do a quick mental nth term test, what happens as n goes to infinity? As n goes to infinity, this is going to 0, right? So, it does not, I cannot use the nth term test because the limit is 0. Okay? All right. So, let's use the, I know if I replace the n's with x's, I know how to find the antiderivative of that. It'll be a little u sub, right? So, let's do the integral test. Well, for the integral test, first of all, say what f of x is. F of x is x over x squared plus 1. And f of x is all for 1 to infinity. F of x is positive for 1 to infinity, continuous because the denominator is never 0, and it is decreasing. And I know it's decreasing again because I just took a mental nth term test and it's going to 0. So if it's positive and continuous and going to 0, very likely going to be decreasing. Okay? Now, I could show you why it's decreasing. We could do a little more math on that, but this is all I need you to show me for this. Okay? And I don't want you to get bogged down with showing me why it's decreasing quite yet. Okay? All right. So we're going to do the integral test. So I'm going to come off to the side and do the integral test. So I have integral from 1 to infinity. Use the same boundaries that are on your sum. X over x squared plus 1 dx. We're going to come off to the side and do a little u sub. So u is equal to x squared plus 1. du is 2x dx. So in place of the x dx, I'm putting 1/2 du. The 1/2 can come out to the very, very front. And then I have just 1 over u du. So it'll be natural log absolute value of u from 1 to infinity, but can't put infinity on my boundary. So we leave a little space and do that, right? Okay, put b in for x and let b go to infinity. Natural log of something going to infinity is infinite. Put 1 in for x. Natural log of 2 is natural log of 2. This is infinite. So this diverges. This diverges. So we found that the integral diverged. Therefore, the series diverges by integral test. Okay. Number 2. Okay, first of all, It's not geometric, it's not telescoping. That plus 1, it's not. Okay. Can I use the nth term test? As n goes to infinity, I'll have 1 over infinity, that's going to 0, so I cannot use the nth term test. So let's use the integral test. We'll have f of x is equal to 1 over x squared plus 1. It's positive, continuous, and decreasing. I need to see that. Tell me what f of x is, and tell me that it's positive, continuous, and decreasing. Do not tell me that the series is positive, continuous, and decreasing. You know why? It's not continuous. It's just a bunch of dots. So it's definitely not continuous. It is positive and decreasing. I'll give you that, but it's not continuous. The function is what's continuous. Okay, so that's what I need to see. Okay? All right. Now we are going to do the integral test. So I'm going to do integral 1 to infinity, 1 over x squared plus 1 dx. Do not forget your dx, please. Okay? Otherwise, you're missing half of your area equation. All right? All right. Now we need to take the antiderivative. Well, the antiderivative of 1 over x squared plus 1 is arctan. So that is arctan of x. That's the most basic arctan. And we want to take that from 1 to infinity. I cannot put infinity. I have to put a b. So limit b goes to infinity of that. Right? Let b, put b in for x. Let b go to infinity. What is arctan of something going to infinity? That's your pi over 2. Minus, put 1 in for x. Arctan of 1 is pi over 4. So this is just pi over 4. This converged. Since the integral converges, the series converges by integral test. You guys, if you stop here and say converges and don't put that, you've only told me that the integral converges. You have not told me anything about the series. We're trying to figure out, does the series converge or diverge? If you stop here, you're only telling me that the integral converged. You've never answered the question. So tell me that the series, you can even write out the word the series, converges by integral test. That's fine. Okay? Number 3. Well, it's not geometric because of the n on the bottom. If it was just e to the n, it would be geometric. It's not geometric. It's not telescoping. Can I use the nth term test? Let n go to infinity. If n goes to infinity, this does not go to 0. This goes to infinity because e to the n, remember, is much stronger in power than just n, right? So I can use the nth term test here. The limit as n goes to infinity of e to the n over n is infinity, not 0. So this series diverges by nth term test. Do not get locked into, just because you're doing a unit on integral test, don't get locked into that. It didn't say that we had to use the integral test. So use the test that works best for you. Number 4 here, find an upper and lower bound of the sum of the series in example 2. Okay? So an upper and lower bound. Here's what that's saying. Here's my series. I want to know 2 numbers that are bounded, that bound this. Okay? So we're using this little piece of information. It's bounded on the left by the value of the integral. So on the left, it's bounded by pi over 4. On the right, it's bounded by that pi over 4 plus the very first term of your series. What is the very first term of our series? 1/2. That's it. Okay? All right. That's the integral test. So we get to practice our integration a little bit. So in class, I have kids turn to example 5 here, and I let them do it. I let them talk it out, and they talk it out and see how this would work. Okay, so if you want to take a pause here and go ahead and try your hand at it, see what you get. This is an example of the way AP could ask it on a multiple choice question. Okay. All right. It says if x is greater than or equal to 1, the continuous function g is decreasing and positive. Positive, continuous, decreasing. When you hear that in order like that, think integral test. Think, I get to use the integral test. Okay? A portion of the graph G is shown at the right. Oh, from 1 to 5. Okay? For n greater than or equal to 1, the nth term of the series is defined by a sub n is g of n. Okay. Again, it sounds an awful lot like the integral test. If the integral from 1 to infinity of g dx converges to 8, so they're saying that this integral is equal to 8, which of the following could be true? Which of the following could be true? Well, remember, the series was looking like that. The series looks like that. Okay? So the series is always higher than 8. So it certainly cannot be 6, and it certainly cannot be 8. Could it be 10, or could it diverge? Well, if the integral converges, the series converges, so it must be 10. It's the only one left. All right. Let's take a look at p-series. Let's take a look at p-series. So a series in the form 1 over n to the p. Remember, n is what's changing. It's the variable that's changing in your series. P is a positive constant. When you see P, think it needs to be positive, okay? And it's a constant. So maybe it's a 2, or a 3, or a 5, or a pi, or a 0.1, or a 2.3. It's a positive constant, all right? If you have a series in this form, it's called a p-series, okay? When p is equal to 1, we have just 1 over n, and that is called the harmonic series, okay? There's a lot of information about harmonic series, and if you are interested in that, go and look it up. It's really interesting, okay? For our purposes, we're not going to go into it too much, okay? Now, I will say you can use the integral test. In fact, we did use the integral test. We use the integral test to prove that the harmonic series diverges, right? We can use the integral test to prove that the harmonic series, this series, diverges, okay? Okay, here's what the p-series test says. And by the way, here, these are both p-series. We used the integral test on them, but they are both p-series. In this one, p equals 1, and in this one, p equals 2. When p is 1, it's called harmonic, okay? And in this one, p is 2, right? When p was 2, our series converged because our graph got to 0 very, very quickly, or it got close to 0 very, very quickly. This one also got close to 0, not quickly enough to converge. It diverged. So ask yourself, if this power is bigger, is it not going to get close? What if it was n cubed down here? Well, if it was n cubed, it would get close to 0 even faster. What if it was n to the 10th? We could go and look on our calculator. I still have these in here. What if we had 1 over x cubed? So we're making p larger. It got closer to 0 even faster, right? And it makes sense because we'd have like 1 over 1, then 1 over 8 instead of 1 over 4, etc. 1 over 27 would be the third term. It gets close to 0 really fast for 1 over n cubed, right? So in a p-series, a p-series converges when p down here is bigger than 1. Think, if p is bigger than 1, our denominator is huge. So this whole thing is going to get close to 0 fast if p is bigger than 1. If p is less than 1 or equal to 1, then the p-series diverges. Okay? So if we had, what if we, instead of doing those two, let's get rid of those two. I'm going to keep the 1 over x to compare it, but let's do 1 over x to the 1/2. X to the 1/2. Let's see what that does. So there's 1 over x. Oh, I think I got rid of that little bouncing thing. Oh well. There's 1 over x. I should have gone back to 10. Oh well. There's 1 over square root of x, or x to the 1/2. That's also going to 0, but it's not going to 0 even as fast as 1 over x did. So clearly it's going to diverge. Clearly this area is going to be infinite, right? So if this p-value is less than 1 or equal to 1, your series will diverge. Okay? All right. It does not. We have no idea what it converges or diverges to. Okay? Next unit, we'll have a way to find the sum of some of these. Okay? But not this unit. So we don't know what it converges to, if it converges. All right. Okay, let's look at some examples. The 3 that's on top does not matter. In fact, if you wanted to, and you would not do this, but if you wanted to, you could take that 3 totally out. And you'd have 3 times something. If this something is infinity, then we'll diverge. If this something is a number, then we'll converge, because we'll be multiplying 3 times the number, right? So the 3 does not affect the convergence or divergence. If it was 3 to the n, yeah, it might affect things. Yeah, could likely affect things. So this is a p-series. What we're left with is a p-series. P is 4, which is greater than 1. We're always comparing it to 1, right? Kind of like a ratio test, but it works opposite. So since p is greater than 1, here's my thought process. My bottom is huge. The whole thing is going to 0 quickly. So this p-series converges. By p-series test. So the 5 I could take out if I wanted to. I'm not going to write it this time, but I could. It will not, the 5 does not affect convergence or divergence. So this is a p-series. What is p equal to? Well, this is the same thing as 5 over n to the what? This is n to the 1, and this, the square root of n is n to the 1/2. N to the 1 times n to the 1/2, you add your powers, so you get 3/2. So p is 3/2. 3/2 is greater than 1. So this series converges by p-series test. P-series is a quick one, not like integral test. Okay? What about this one? Another p-series. What is p? P is 1/3, because I could write that as n to the 1/3. And 1/3 is less than 1. Right? So this series diverges by p-series test. Again, my thought is that n to the 1/3, it's a small, yes, the whole thing is going to 0, but just not very fast. Even slower than 1 over n goes. Okay, what about this one? It's a p-series where p is 1, so we have a harmonic. Okay? You don't have to tell me that it's harmonic. You can just say p is 1, and that's fine. So this series diverges. You can say by p-series test, or you can say diverging harmonic series. You can say either one of those. They're the same thing. You can spell series right. Okay. All right, one more over here. It's another p-series. Again, the -2 does not matter. You can just take it out. If it's just a number, you can just factor it out. Okay? It's another p-series. P is 0.995. How does that compare to 1? Well, it's less than 1. So this series diverges by p-series test. Okay? Most students like the p-series test. I know I like the p-series test. It's short and it's sweet. So that's the p-series test. All right, your turn to go practice. Now you have 5 convergence, divergence tests. So they're going to start to get a little bit mixed up. So I hope you're staying on top of your assignments, your practices. Do not wait to do all of these till the day before the test. You will be sorry that you did. Okay, have fun.